Greetings, everyone. Welcome back into trigonometry. Time to take a little side step and talk about test number 3. We've finished the third unit, which might feel like a small unit, but it's jam-packed with lots of details. And just as before, I wanted to work out some of my old tests, kind of a conglomeration of two different ones in this case. And as always, I'm going to stress to you that you don't study just these problems, that it's always about the skills themselves and the problem-solving procedures that go along with being prepared for the type of problems that we are approaching. So, test 3 review for trigonometry is all about verifying identities, unfamiliar identities, basically going through the steps that it takes to prove that an identity is true. Maybe in the homework, a few of them may have been false to give good practice, but on the tests, we typically always put ones that are true, just so that you can not get totally confused in a small amount of time, We are going to be talking about solving equations that have trigonometric functions in them, and using the advanced identities, specifically sum and difference of angles, double angle and half angle identities. Also mixed in with the half angle, you'll probably be familiar with the power reduction identities. But typically these are the three main categories, and it's really just to give you that next level of advanced identities that trigonometry uses. There's thousands of actual trig identities out there, and we just want to broaden the mind of people who approach trigonometry. Okay? Let's begin with verifying a couple of identities that I've put on several tests. These are both identities I find to be not basic, but not too advanced that they take a whole lot of time on a test either. So that these are kind of like right in the middle, perfect spot for tests, or other ones in the similar fashion and similar structure. 2 cosecant x minus 2 sine x equals 2 cosine x times cotangent x. Just, obscure enough to not be obvious. But what I can do is I can set up one side to start looking like the other. But most of the time when I have things like this, I like to work a little bit of both sides. And what it does is it just saves me some time and some space on the paper. Okay, so here what I'm going to start with is I'm going to rewrite cosecant x as its reciprocal, 1 over sine x. And the 2 is multiplied. So what I really have is 2 over sine x minus 2 sine x over 1. And then this is equal to 2 cosine x times, now cotangent is equal to cosine x divided by sine x. And I'm converting to that just to make the right side simpler and easier to approach. Okay, so then on the right hand side, I'm going to have 2 cosine squared divided by sine x. And that's where the right side is going to rest. On this side, however, what I want to start doing is combining these two fractions. So in order to do that, I need a common denominator. Between sine x and 1, that's sine x. So I'm going to multiply sine x here and here in order to facilitate that common denominator that I need. So what I end up with is 2 over sine x minus 2 sine squared x over sine x. And now that these two have a common denominator, I can combine the numerators. And this is what I mean by combine. Notice that they both have a 2. I'm going to start by factoring that out. 1 minus sine squared, like this. Okay? Now the right-hand side hasn't changed. It's not going to. And we're actually just one step away now. From our Pythagorean identities, 1 is equal to sine squared plus cosine squared, right? So for the 1 right here, sine squared x plus cosine squared x is one way of looking at it. Or you can just remember that 1 minus sine squared is equal to cosine squared. Either way, if I put sine squared plus cosine squared for 1, the sine squareds will add out. And that leaves me with cosine squared in the numerator. And therefore I have 2 cosine squared x over sine x is equal to itself. Check, it's verified. Okay, next, secant of x times the quantity 2 sine x minus cosecant x is equal to the quantity of tangent x minus cotangent x. Okay, now as usual, there's several ways you could approach this. I've seen some people distribute the secant x in to try and accommodate that, because secant times sine does give tangent. Okay, in this case though, I'm going to combine these in the center here in order to make this work better for me. Okay, so here's what I'm going to do. I'm going to work both sides, but I'm also going to combine these two. So secant x, I'm going to keep as secant x for now, just because it's quicker to write. And on the inside here, I've got 2 sine x over 1 minus 1 over sine x. Very, very familiar, right, to the last one? And for tangent and cotangent, I'll write tangent as sine x over cosine x, and cotangent as cosine x over sine x. Right? Those are also a couple of identities, the quotient identities there. Right? Okay, so just as before, I'm going to do the common denominator here by multiplying sine x, right, times sine x here and times sine x here, in order to get the common denominator there. And a very similar result is going to occur. So I have secant x times 2 sine squared x, right? And it's over sine x. So then it's minus 1, like this. Okay, on this side, if I can combine those two fractions, it would make it easier for me working on this side as well. So here's what I'm going to do there. I'm going to multiply and get a common denominator. On this side right here, I'll multiply sine x here and here. So that'll give me sine x times cosine x. And over here, I'm going to multiply cosine x in both spots. And that'll give me sine x cosine x, which is the common denominator. Okay? So then, with that common denominator, sine x times cosine x, I now have sine squared minus cosine squared. Okay? Well, we're almost done. Instead of secant x here, I'll go ahead and convert him now. I'm going to say, look, this secant x, instead of writing secant, that's the same thing as 1 over cosine x times that. So then from here, my denominator is going to be sine x times cosine x, right? Because I could just multiply straight across with those denominators. And 2 sine squared x minus 1. Well, if I were to replace the 1, let's say, with sine squared plus cosine squared, right? Like right here, for the 1, right? That'd be sine squared minus, plus cosine squared, like that. Don't forget, though, that it's minus. So technically what we're saying is that this will be negative sine squared minus cosine squared. Okay? So I have 2 sine squared minus 1 sine squared, which is going to leave me with a singular sine squared. And then I've already got the minus cosine squared that didn't combine with anything. Notice it's the same as this side over here. Therefore, it is verified. An alternate idea here to this last step, one may have noticed that sine squared minus cosine squared is equal to negative cosine of 2x. Ooh, yuck. Yuck, 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 yuck. Not supposed to use your hands on the board. Negative cosine 2x over sine x cosine x, like that. Okay? So at this point, you could also have argued the same thing here. Normally, cosine 2x is 1 minus 2 sine squared x. So you could actually argue this being the same thing through the same advanced identity. I did it the other way originally with this because it uses the basic identity. Pythagorean identity, sine squared plus cosine squared is 1. Okay? But if you can remember the more advanced identities, the double angle in this case, then you could have also used that as a finale step for that particular identity. But either way, it is 100% verified there. Now let's begin the little section on solving equations that involve trigonometric functions. So I've got 5 plus 19 sine theta is equal to 2 sine theta minus 7. Obviously, I have some algebraic steps first, and then I can handle the trig function. The good news is that it's all the same trig function, so I can group them all together like terms. So just as your typical algebraic equation, I'm going to get rid of one type from each side. So I'll get rid of the sine from here, which is going to cause me to balance it there. And then I will also get rid of the 5 here, which will cause me to balance it there. Alrighty. So then my equation becomes 17 sine theta is equal to negative 12. So from here, I just have to divide by 17. Negative 12 17ths. Okay, so now I can switch modes to trigonometry. I want to do the opposite of whatever sine is, but I have to remember sine is a periodic function, and therefore I'm going to get several answers. Notice this just says solve. It does not restrict me in any kind of way to the 0 to 2 pi or anything else like that. So they want all possible answers. There's an infinite number of those in the case of our trig functions here. So then what I do is I pick up my two pieces of information. Where is sine negative? I know that that's going to be quadrant 3 and 4. And then also, what is the reference angle to go along with a sine ratio of 12/17? Okay, so I say that my reference angle must be the inverse sine of 12/17. Notice I did not use the negative in the reference angle. Okay, so since this is theta, I'll go ahead and do this one in degrees. So if I have my calculator set in degree mode, I'm going to do the inverse sine of just 12/17. And that gives me 44.9 degrees. Okay, so now I've got my reference angle. I'm going to now apply that reference angle to the two quadrants that were listed. Alrighty, so then that means that my theta value is around about equal to 44.9 degrees in quadrant 3. Okay, so remember, for quadrant 3, let me go ahead and separate this out here. Good. All right, so for quadrant 3, remember that my angle is here. This is the full angle, and my reference angle is here. Okay, so my actual answer here is going to come from 180 degrees plus the 44.9 degrees. Okay, and I need to consider that it's all possible solutions. So this is a starting point, and then I have to say plus 360n, and then I'm going to qualify my n. N is an element of the integers. This is going to be true for the rest on out, so I don't have to keep rewriting it. Okay, so let's simplify this here. I have theta is approximately equal to, this is going to be 224.9 degrees plus 360 degrees times n. Okay, so here is one set of answers. That's an entire set, an infinite set actually, right? It's for any integer n, could be any whole number, positive, negative, or zero. Okay, or theta could also be approximately, now remember for quadrant 4, our angle is here, and our reference angle is here. So I will be doing 360 degrees minus the reference angle, 44.9 degrees, like so. And of course, I'll still be adding in the cyclic extension to get the rest of the answers there. And then we'll simplify. 360 degrees minus 44.9 is going to give me that theta is approximately equal to 315.1 degrees plus 360n. And here's the other infinite set of solutions. So together, both of these two make the entire infinite set of solutions for this particular equation. Okay? Next, secant of y times tangent of y is equal to 2 times tangent of y. And this is not an obvious one right away, unless you're just looking out for what I'm about to show you. I see the repetitive tangent there, and I don't want to just get rid of it. Tangent is contributing something to this equation. So I'm going to bring all of my terms together and factor it so that I can solve it separately. It's difficult to do more than one trig function in an equation, but if I can separate them, I avoid that problem, that issue. Okay, so I'm going to subtract. I have secant of y times tangent of y minus 2 times tangent of y is now equal to 0, just by subtracting 2 tangent y from both sides. At this point, I can factor a tangent y out. And since this is a multiplication and the result of that product is 0, I can split these two into two separate equations. I can solve then the fact that secant y minus 2 is equal to 0, or tangent of y is equal to 0. So this equation right here tells me secant of y is equal to 2. And to make it easier on myself, I'm going to reciprocal both sides. That's completely okay because it's not going to cause any division by 0. I'm not crossing over any values of y that would do that. So cosine of y, the reciprocal, would then be 1/2. So we actually know the solutions here, right? I'm mixing the two pieces of information here. One of them is the quadrants where cosine is positive, right? That's going to be quadrants 1 and 4. And cosine with a 1/2 is a reference angle. I'll do radians this time since we're a common letter of y, not a Greek letter. My reference angle is the angle that has a cosine ratio of 1/2, right? That's pi over 3. 60 degrees, pi over 3 radians, right? Okay, and I'm applying it to quadrants 1 and 4. The first one's quite obvious, right? Quadrant 1 is itself. So y is going to be equal to pi over 3 plus 2 pi n. Okay, so there's one solution set. I'm going to go ahead and qualify my n as any integer here. And it's going to apply here, it's going to apply over there in just a second, and it's going to apply, down here for this next one. In quadrant 4, don't forget that I will be doing the full rotation, in this case 2 pi minus the reference. So I have or y is equal to 2 pi minus the reference angle pi over 3 plus 2 pi n. That's my other option, right? This is the quadrant 1 option. This is the quadrant 4 option. So then it simplifies down into 5 pi over 3 plus 2 pi n. And of course, n is allowed to be any integer value, which is what makes this an infinite set. N could be different values. Okay, and then the other one. Or it could have been when tangent of y is equal to 0. So that's more potential solutions for y. Now this one, I'm not really going to even look at it as a reference angle thing. This is one of those quadrantals, right? Tangent of y is equal to 0 at 2 places in a normal cycle, but I can actually group them together as most tangent equations you can. Okay, y is going to be equal to 0 radians. And then it also happens at pi radians, 180 degrees, plus pi times n. It happens at pi, and at 2 pi is at 0 again, then 3 pi. Everywhere that you land on the actual x-axis in your rotation. So then this simplifies to just y is equal to any multiple of pi, basically. Pi times n. Okay? So next we discuss what happens when you have a trig function acting on something other than just the variable by itself, which can happen in a lot of the functions we've graphed. And these equations would be good examples of what would happen if you needed to find a particular value on a graph, or more specifically, maybe an intercept on a graph, or maybe where two graphs are intersecting. Who knows? These are good equations that would be more generic examples of that. So let's jump right in. 14 times the sine of 3 times x. And remember, there's actually an understood parentheses here. The 3 is attached to the x. I cannot divide by that 3 while it's still inside of the sine. Big mistake that I see happen a lot. Don't divide by 3 before you get rid of the sine. Plus 8 equals 1. Okay, so we have a little bit of algebra first. I'm going to need to get rid of the 8. So I'm going to subtract it from both sides, right, as you would expect. Minus 8, right? That's going to give me 14 times sine of 3x is equal to negative 7. Dividing both sides by 14 is going to land me into sine of 3x is equal to negative 1/2. 7 over 14 reduces to 1/2, right? Okay, so now I've got to get rid of the sine. It's not just as simple as, oh, just slap an inverse on there. Remember, periodic functions have those whole list of solutions, and I'm solving in a particular domain restriction. So I need to be very careful how I do the inverse here. I need to make sure and be generic at first, and then bring it down into the interval the appropriate way. So I'm going to associate sine with the negative, right? That's going to give me quadrants 3 and 4 again. And then I'm also going to associate sine with the 1/2. Okay? We'll do this one in radians, yeah. We'll do them both in radians. They're both x's. Let's just do that. It's in radians there, so that's the reason why I'm going to default to radians here, because it was pre-listed that way. So now, when I'm getting rid of the sine, don't forget, I didn't solve for x yet. What I'm doing by getting rid of the sine is solving for 3x. So 3x is going to be equal to one thing, or 3x is going to be equal to some other thing. In fact, let me put those side by side this time so that I have more space for solving. Okay, now the angle whose sine is 1/2, that's going to be my reference angle, right? My reference angle here is going to be pi over 6. So then from here, quadrant 3, pi over 6, I'm going to have pi plus pi over 6 is the starter answer, right? But then I've got to do plus 2 pi n, because 2 pi is the period for sine. Okay? Or if I do the reference angle pi over 6 in quadrant 4, that's going to be 2 pi minus pi over 6. And then, of course, still plus the 2 pi n. So then I'll simplify this. This is going to give me 7 pi over 6 plus 2 pi n. And then to solve for x, I need to divide by 3. Be careful when you're dividing here. The division by 3 needs to be done to both of these pieces. So some people prefer to think of it as times 1/3. That's fine. Times 1/3, times 1/3, whatever works for you. Okay, so then I'm going to end up with x is equal to 7 pi over 18 plus 2 pi over 3 times n. Now, of course, don't forget, n in this case is some number in the integers. This statement right here, by the way, doesn't mean that n is every value of the integers, but n is restricted only to being from this set. In our particular predicament that we're in right now, it's actually not going to be the entire set, because in a minute we're going to have to restrict down to whatever fits in the 0 to 2 pi listing. Okay, so now let's do the other one here. I'm going to have 3x is equal to, this is going to be 12 pi over 6 minus 1. I have 11 pi over 6 plus 2 pi n. Same as before, I'm going to divide by 3, and therefore x is going to be 11 pi over 18 plus 2 pi over 3 times n. N is still restricted to the integers. To make this easier on myself, because now I have to start plugging in values of n. If the instructions didn't restrict me, right, we could stop here and say, hey, look, this is the infinite list. You pick any value of n you want. But that's not true for us. Only certain values of n are going to make this true. So what I'm going to do is I'm going to actually combine these with a common denominator here. Okay? right here, if I do times 6, okay, and actually I'll go ahead and do it for both. I'm going to do times 6 here and times 6 here. Times 6 here, times 6 here. And this is really just to make it easier for me to do the next step. Instead of having to do this every single time, what we'll notice is that there's a pattern to it. Okay? So all this is an alternate way of writing the generic answer. Okay? So I've got 7 pi plus, this is going to be 12 pi times n. Okay? Over 18. You want to make it more generic? Do this. Take the pi and factor it out. So that what I've got is 7 plus 12n times pi. So why is this easier? Now I'm just working with these whole numbers here. Every one of them is going to have a pi over 18 once I plug in some value of n. And notice I can do the same thing here. X is going to be equal to, I'm going to have 11 plus 12n, and I factored out the pi over 18. Okay? At any time up to this point right here, we could have still said that this is the generic solution. Okay? You could actually rewrite any generic solution this way. All it does is it makes it easier to plug in values of n. So let's start listing out the actual answers here. Okay? So, x is going to be equal to, all right, I have to go between 0 and 2 pi. So, when n is 0, I'm going to get an answer from each one. When n is 0, I get 7 pi over 18 and 11 pi over 18. 7 pi over 18, 11 pi over 18. That's when n is 0. Okay, next, when n is 1, okay, 7 plus 12 times 1, that's 19 pi over 18. And 11 plus 12 times 1, that's 23 pi over 18. That's when n is 1. Okay? Notice I still haven't gone over 2 pi yet, because with an 18 denominator, that would be 36 on the top. So I'm going to keep going. When n equals 2, right? So if I plug in 2, that's 24 plus 7, which is 31 pi over 18. Still not bigger than 2 pi. And right here, if I plug in 2, that's 24 plus 11, which is 35. Still not bigger than 2 pi, because 2 pi would be 36 over 18. So both of these come from n equals 2. Now I want you to notice that we're really, really close to 2 pi here. If you plug in the next one, n equals 3, you'll notice that the first one is bigger than 2 pi. If I plug in 3, that's 36 plus 7, okay, which is 43 pi over 18. That's bigger than 2 pi. So these 6 values here, these are the 6 solutions that are within the 0 to 2 pi restriction. And it should make sense to you. I did 3 entire cycles. And notice our frequency is 3x. So I'm doing 3 whole cycles, and I'm getting all of the solutions there. And then they're shrunk down into the 0 to 2 pi domain there. Okay. Next, 15 times cotangent of 5x over 3 minus pi over 7. And then that whole thing minus 11, and it equals 4. So just like before, I can't handle anything in here until after I've gotten rid of the cotangent, which means I'm going to have some algebra first, right? Then I'm going to have to handle the trigonometry. Then I'm going to have a little bit more algebra just getting to the x. So the first things first, I'm going to add the 11 to both sides. which gives me this. I'm going to divide both sides by 15. Okay? Dividing both sides by 15. I'm gonna cheat a little bit here because I have on a marker board. 15 divided by 15 is 1. All right. Now let's handle the trig part. The trig part is that I'm dealing with cotangent is being positive and cotangent is equal to 1. Now most of the time I would go ahead and say, let's do the reciprocal and turn it into tangent, but this one's very, very straightforward and obvious. And also it's equal to 1, so the reciprocal is the same either way. Cotangent and tangent are positive in quadrants 1 and 3. Okay? However, I'm not going to have to do two separate pieces like I did here, because cotangent's period is also only pi, which is exactly the difference between quadrants 1 and 3. So I'm only going to do the quadrant 1, and the quadrant 3 will get included because of the period being pi. The quadrant 3 will automatically be included if I just do pi n instead of 2 pi n. If you wanted to separate them out and do the two separate ones, you could. It'd be no big deal. Okay, what about the reference angle? The cotangent with a ratio of 1, reference angle, pi over 4. 45 degrees has a tangent of 1, so its cotangent is 1 also. Okay, so what does this mean? I have 5x over 3 minus pi over 7 is equal to pi over 4, basic answer, plus generalize pi n. Okay? So I've got the generic answer. Think of it this way. It's theta equals the same thing that we've been doing. But now instead of theta, I just have this big chunk that was inside of the trig function. I'm going to leave it generic, and I'm going to say n can be any integer for now, until I get to the very, very, very end, and I start plugging in values of n to see where I'm at in that domain, the 0 to 2 pi stretch. So I'm going to just start solving for x here. I'm going to add pi over 7 to both sides. Okay, now look right here. Pi over 4 plus pi over 7. I'm going to do that with a common denominator of 28. That's the same thing as 7 pi over 28 plus 4 pi over 28. Because I'll do times 7 and times 4 and times 4. Altogether, that's going to give me 11 pi over 28. Okay, so that's where I'm at now. 5x over 3 is equal to 11 pi over 28 plus pi n. And of course, n is still restricted to any integer. To finish solving for x, I'm going to multiply 3/5. Right? Do times 3/5 to get rid of both. So that means I have to do times 3/5 here and times 3/5 here as well. I'm going to go ahead and get a jump on consolidating these, and I'm going to say let's also do the common denominator, which is going to have a 28. So I'm also going to do times 28 over 28 to that one, so that I can bring it all together. Okay, so x is equal to, I've got 33, right? 33 pi, but I'm going to factor out the pi. And in the denominator, I've got 5 times 28, which is 140. And then over here, I just have pi times n, right? So the n is going to be here, and I'm factoring out the pi. 3 times 28 is 84. So plus 84n. Okay, let's go through that one last time. I did 33 pi, right? And then I have 84 pi. But I factored out the pi, right? And the 84 was times n. The denominators are the same. They're both 5 times 28, which is 140. And remember, I do that just to make it easier to plug in the values of n. Okay? Now, I have a really kooky looking frequency here, 5/3. That's a bit bigger than 1, right? It's actually almost 2. So I'm going to have more than a normal cycle's worth of answers, but it was shifted. It was also shifted with that pi over 7 there. Well, it's not exactly the shift, but anyway. So now let's just go ahead and start plugging in values of n and just see where we land. We need to be between 0 and 2 pi. Okay? So here we go. X is equal to. Now at this one, I'm only getting one value per n. So every time I put one down, that's another count for n. I'm going to start with n equals 0. Okay? N equals 0 is going to be my first one. And then it's going to go 1, 2, 3, on out. Okay? So when n is 0, I just get 33 pi over 140. Okay? Now keep in mind that I don't want to go over 2 pi, which means I need double on the top. Double of 140 is 280. Okay? So I have to stay less than 280 in the numerator. Here's the pattern. I'm going to add 84 every time n goes up. So when n is 1, I have 84 plus 33. When n is 2, I'm just going to add another 84. Okay? So I've got, 117 pi over 140 is the next one. When n equals 2, just add another 84 to this. That'd be 190 plus 11. So that's 201 pi over 140. Okay, next. If you try to add it again, let's see, n equals 3, right? Add 84. That's going to be 285 pi over 140. Well, double of 140 is 280. So I can't have this one. These three right here are my solution that's within the restriction. Okay? It's n is any integer up until this point. And then when I start plugging in the values, you can see exactly where we need to be. All right? To finish off this section on equations here, let's look at some of the more advanced structures that go with these. These are both quadratic types. And not only that, but these are sort of the upper half of the middle when it comes to the quadratic types, because I don't have the same trig function immediately right away. I have to use the Pythagorean identity to fix this. Okay, so here, sine squared, and I have cosine. So in this one, in order to make the quadratic work perfectly like we like, I'm going to change the sine squared into something with a cosine squared, because it's easier to do that than to try and change the cosine theta into something that involves just sine. So then I just remember that right here, sine squared is the same thing as 1 minus cosine squared theta. And then I'm going to distribute the 2 in. So then my next step looks like this. I have 2 minus 2 cosine squared theta plus 11 cosine theta is now equal to 7. And since this is a quadratic, what I would prefer is to have my squared term positive. So here's what I'm going to do. And this is sort of unorthodox, but I'm going to subtract and add and do the opposite of each one of these to get them over on that side. Okay? So bear with me. I'm going to minus 2. I'm going to plus 2 cosine squared theta, and I'm going to subtract 11 cosine theta from both sides. So minus 2 plus 2 cosine squared theta minus 11 cosine theta from both sides there. So that means that now on my left-hand side, I'm having an equal sign shift here. I now have 0 on the left-hand side, right? I'm shifting to here. And I'm going to put it in order of descending exponent. 2 cosine squared theta minus 11 cosine theta. And 7 minus 2, of course, is 5. Okay, so from here, you can either try to factor or you can use quadratic formula. Personally, when it comes to being efficient and saving time, I prefer to just avoid playing anything that's sort of like a game or anything like that. If you don't see factoring right away, then it ends up being more like playing a game with numbers. And sometimes you can lose some efficiency that way. And in a time test, you want to try and go straight for something. And if there was going to be one method that just works all the time, it's going to be the quadratic formula. So you should pick that as like your basic. Practice one method all the time, and then that is something that you can be guaranteed to be good at, right? So right here, this is exactly what I'm going to do. I'm going to use the quadratic formula, and remember in this case, it's not of theta. The cosine of theta is the thing that's being squared here, right? So when I'm using the quadratic formula, 2 is my A, negative 11 is my B, and 5 is my C. And I'm solving for cosine theta, not theta yet. So negative B plus or minus square root B squared 4AC, right? That's not a 15, that's times 5, all over 2A. Okay, so then this is going to be equal to, I have 11 plus or minus, and then I've got 121 minus 40, right? Because 8 times 5. 121 minus 40 is 81 over 4. Okay, so then this is going to be 11 plus and minus 9 over 4. So I can do 11 plus 9 over 4, right? Let me go ahead and write it out. That means my cosine theta is going to be 11 plus 9 over 4, right? Which is 20 over 4, which is 5. Or cosine theta is going to be 11 minus 9 over 4, right? Which is 2 over 4, which is 1/2. Now right here, I'm hoping that you recognize this right away. Cosine theta equaling to 5 is non-real. Because sine theta and cosine theta specifically are restricted to being in between -1 and 1 for planar trigonometry, okay? We don't go above the 1 or below -1 when it's equal to a sine theta or a cosine theta. There are no real angles that are going to give you this result, okay? So this is as far as this goes, okay? So we stop here. This one, however, we can quickly get the solutions for, right? I'm doing where cosine is positive, so that's going to be quadrants 1 and 4, right? Cosine with a positive is quadrants 1 and 4. And then cosine with the 1/2 there is going to give me a reference angle of, we're doing theta, so this is degrees. Theta is going to be 60 degrees. Quadrants 1 and 4 for 60 degrees. So theta is going to be 60 degrees, or theta is going to be, in quadrant 4, that would be 300 degrees. right? Because it's 360 minus the 60. Okay, plus 360 degrees times n for both. Because it just said solve, so it's finding all of them. And of course, at that point, n has to be qualified as any integer. So then this is my solution set here. Okay. Same idea on this guy over here. I've got two different trig functions, so I need to convert one of them. And of course, the easier one to convert is going to be the guy that already has the squared on it, right? Now, cotangent is related to cosecant. Remember, the original Pythagorean identity for that is cotangent squared of x plus 1 is equal to cosecant squared. But all I have is cotangent squared there. So instead, I'm going to manipulate this. Cotangent squared x is going to be equal to cosecant squared x minus 1. Right? So right here, that's exactly what I'm going to do. I'm going to take this negative 3 times cosecant squared x minus 1, like that. And of course, this is still the same. I then distribute the negative 3. So I have negative 3 cosecant squared x plus 3. This side is still the same. Now I have an equation of just things in cosecant. Again, I like to have the squared positive, so I'm going to add this to the other side. And then, of course, that means I'll have to move the 3 so that I can have my equals 0. Put it in all the descending order there, so I have 3 cosecant squared of x plus 7 cosecant of x plus 2. Alrighty. Now, like I said before, if you don't see the factorization right away, then you end up blowing a lot of time on that. But since I did the quadratic formula on the other one, I'll go ahead and do the factoring on this one. I know that it's going to be a 3 cosecant times a cosecant. And I also know that there's going to be a 1 and a 2. And it's going to have to be here and here, so that I can do 3 times 2 is 6, and 1 times 1 is 1. 6 plus 1 is 7. Everything's positive, so this is going to be positive and positive. Okay, so I can get my factorization on that one pretty quickly. The numbers were small enough and it worked out nice. Now, right here, since this is equal to 0, I can split it into 2 equations. Here I'm getting 3 cosecant of x plus 1 is equal to 0, which tells me that cosecant of x is going to be negative 1/3, because I'm going to subtract the 1 and divide by 3. Remember, when it's cosecant, we prefer to switch to sine. So this tells me that sine x is equal to negative 3/1, because I'm doing the reciprocal. And again, this is beneath negative 1. Okay? So non-real. You should stop here. Okay, what about this one? Cosecant of x plus 2 is equal to 0, which means cosecant of x is equal to negative 2 when I subtract 2 from both sides. Do the reciprocal. Sine x is going to be equal to negative 1/2. Alrighty. This one we can solve very similar to the other one, right? I'm just going to be doing the different quadrants, right? This one seems to be a recurring theme, right? Sine with a negative. We've done this one several times. Quadrant 3 and 4. And then sine with the 1/2 is going to give me a pi over 6. Okay? So let's just go ahead and write out the 2 solutions here. I have that x is either pi over 6 plus 2 pi n, or x is going to be In quadrant 4 with pi over 6, that's going to be 11 pi over 6 plus 2 pi n. And of course, n is any integer. Right? Now we finish up the test with talking about the advanced identities. The half angle, the double angle, the sum and difference identities. On rare occasions, even in trig, we'll talk about the power reduction identities. But these are two problems that I put on lots of different tests because they both test the two different sides of using these things commonly. The first side is to calculate actual values of angles that are not themselves memorized angles, but we can still calculate the result exactly. And the other side is talking about some generic angle and getting to some other angle using the original one as a corridor. Okay, so here we go. Compute or calculate the exact value using a certain identity. We want to calculate the tangent of 105 degrees using the half angle identity. Well, if I'm using a half angle, remember what that means is I need to rewrite the 105 as a half of something. Well, 105 happens to be half of 210. 210 degrees is one of our quote-unquote memorized angles via reference angle. 210 is the quadrant 3 angle whose reference is 30 degrees. Okay? Now, what I'm going to do here is I'm going to use the tangent half angle identity. There's three different ones, but the one I'm going to use is the 1 minus cosine of 210 over sine 210. So you see, once I rewrite it as the half angle, then that's when I can apply the half angle formula. The cosine of 210 is just like the cosine of 30, because that's its reference angle, but cosine is negative in quadrant 3. Sine of 210, just like the sine of 30, but again negative because it's in quadrant 3. So then this is going to be equal to 1 minus the cosine of 30 is square root of 3 over 2, but cosine is negative in quadrant 3. And then again, the sine is negative 1/2. And so from here, what I would do is I'm just going to multiply by 2, because that's the common denominator. So I'll do times 2 here, times 2 here, times 2 here. And that is going to result in 2 plus, because of the double negative here, square root of 3 over 1 over negative 1. Okay? So then I can write this as negative 2 minus the square root of 3. All right. Next, cosine of 11 pi over 12 using a sum or difference. Okay? Let's go the easier route of using a sum. Remember, the cosine of a sum, right? I would want to write it as cosine of a plus b. That's equal to cosine a cosine b minus sine a sine b. And so I just need to figure out two things to separate the 11 pi over 12 into that would be easy sines and cosines for me to figure out. Okay? So right here in this next step, I'm going to have cosine of two things. Since this is a denominator of 12, I'm going to pick two things with a denominator of 12. The pi is just going to be shared, pi and pi. Now I need two numbers here that add up to 11, but I would like these to simplify into angles that I'm familiar with. I would like these to simplify into two angles that I could quickly get the sine cosine for. Okay? So I need things that are multiples of those sorts of things, right? So for example, right here, I could do a multiple which is 8 and 3, right? Now 3 pi over 12, 3 and 12 will reduce to give me pi over 4. Pi over 4 is 45 degrees, right? 8 is a multiple of 4, right? That's why I picked it. 8 is a multiple of 4, and so is 12. So that would give me 2 pi over 3. Pi over 3 also being one of the known angles there. And 2 pi over 3 is just one of the angles that uses it as a reference. Okay? So that's what I'm going to do. I'm going to rewrite it as these two. 8 and 3 add up to 11. So that would really be cosine of 2 pi over 3 plus pi over 4. Okay? Now again, remember, these are two of the known angles now because these have the denominators that we're familiar with. This is going to be something relating to 60 degrees, and this is going to be 45 degrees itself. Okay? So I'm going to split this into the cosine of 2 pi over 3 times the cosine of pi over 4 minus the sine of 2 pi over 3 times the sine of pi over 4. So then that right here, remember what it said, this is related to 60 because it's over 3. Okay, but 2 pi over 3 is going to be in the second quadrant. Cosine is negative in the second quadrant. Okay, but cosine of 60 is a half. So I've got negative half. And of course, cosine of pi over 4 is square root of 2 over 2. Minus sine in quadrant 2 is positive, and sine of 60 is square root of 3 over 2. And pi over 4 is square root of 2 over 2, sine or cosine. Okay? So then we can simplify this. And notice what I'm going to get is a negative square root of 2 over 4 and a negative square root of 6 over 4. So it's minus square root of 2 minus square root of 6 all over 4. And that's my exact value there. All right. Lastly, sine of 300 using a double angle. So just like before, if I'm going to use it, I need to rewrite it as what the name suggests. So 300 is double of something. All right, let's do that. Sine of 2 times 300 is double of 150, like this. Okay, but of course the sine of 2 times an angle, right? We have the identity for that one also. Sine 2a is 2 sine a cosine a. Okay, so then I have that this is going to be equal to 2 times the sine of 150 times the cosine of 150. 150 has a 30-degree reference angle in quadrant 2. So this is 2 times 1/2, because 1/2 is a sine of 30. Sine is positive in quadrant 2. Cosine is negative in quadrant 2. And cosine of 30 is square root of 3 over 2. 2 times 1/2 is 1. And then 1 times anything is itself. So notice I'm getting negative square root of 3 over 2 for this angle right here. Which we probably already knew that one, right? Because 300 is one of our directly memorized angles. It has a reference angle of 60. Sine of 60, square root of 3 over 2. So, see, it works out. Okay, so enough of the direct calculating. Here's the flip side. What if I have some information about some angle that I don't know, and with this information, calculate something about other angles that are directly related? Now notice, this is not the same angle as this. This is half of that angle, right? And this is double of that angle. These are technically other angles, different angles. And I'm going to calculate these trig ratios using the information on the original without using inverses. And that's the key here. We want to get exact values. We want to calculate them exactly, okay? Not approximate them with a calculator. Okay, if you wanted to do the inverse stuff and solve for phi the way we solve for it in equations, and then plug it in down here somewhere else and then punch it up, I mean, of course you could do that. You would get a decimal approximation, and that's not the spirit of this particular problem. This problem wants you to advocate on using these identities. So I start, first of all, by gathering the information about phi here, right? I've got the cosecant of phi. I'm going to use that and this to gather even more information that's staring at us, and it's just not in a obvious form yet. Okay? So I've got phi in quadrant 4, and I'm going to draw it out. Always a good idea to draw it out. Phi is an angle in quadrant 4. So this is phi right here. Right? This is angle phi. Of course, the reference angle for phi is going to be in here. We don't really care what that really is at this point. And I'm just going to draw the triangle for it here. The cosecant means that this must be the hypotenuse, right? Or r. And cosecant is reciprocal of sine, so this must be the opposite, or y. And since we're in quadrant 4, right? That's what this says, since we're in quadrant 4, then that means the negative should be applied to the y value. This is going to be negative 13, the hypotenuse being 20. Okay, so then I can use my Pythagorean identity, right? 20 squared should be equal to negative 13 squared plus whatever x is up here squared. Okay, so that's 400. And then this is 169. I'm going to subtract 169 from both sides, and that's going to give me what x squared is going to be. So let's see, that should be what, 231, right? And so I'll say that the square root of 231 is x. Notice I picked the positive because of where I'm at. This should be the positive square root of 231. Can we reduce that any? Because I see 3 goes into this. 77. Okay, so 3, 7, and 11. That's, yeah, we don't need to factor that down any. Square root of 231 is thusly my other side to the triangle there. Now, once we're here, I can get any information I need about phi and feed it to these other problems. Okay? Now, sine of a half of something. That's the guy that has the plus or minus in the formula, right? Sine of a half angle, sine of half of A, let's say, is plus or minus square root 1 minus cosine A over 2. Okay, I've got that plus or minus that I've got to deal with in this identity. So I need to know beforehand, before I compute this sine, I need to know what quadrant, not phi, but what quadrant this angle 1/2 of phi is. Simple enough. I'm going to multiply by 1/2 here. Okay, so then if I do times a half, times a half, times a half. Notice it tells me that 3 pi over 4 less than or equal to 1/2 phi less than or equal to just pi because it's 1/2 times 2. This tells me something about the angle 1/2 of phi. It's between 3 pi over 4 and pi. It's less than pi. This is quadrant 2. Phi is in quadrant 4. 1/2 of phi is in quadrant 2. Sine of a quadrant 2 value is going to equal a positive value. Therefore, the decision has been made for me, right? I now know that I will be using the plus, not the minus, and I'll be doing the square root of 1 minus the cosine of phi over 2, right? Because phi is my angle there. The cosine of phi, that's the square root of 231 over 20. So I have the square root of 1 minus the square root of 231 over 20 all over 2. Okay, let's simplify that a little bit. What I'm going to do is I'm going to multiply by 20 on the inside, times 20 here, times 20 here, and times 20 here. So that simplifies it a little bit. That gives me the square root of 20 minus the square root of 231 all over 40. Now, depending on how much you really want to pick at this scab here, you could go further. But to be honest with you, this is not a bad place to stop. And it is an exact value, not necessarily a nice one. It's a nasty nested square root, but it is an exact value of that particular trig ratio. Okay, next, tangent of 2 phi. I'm just going to use the double angle identity for tangent, right? Tangent of 2 phi. In fact, instead of just writing it there, I'm just going to write out my formula here. That's 2 tangent phi over 1 minus tangent squared phi, right? So what is tangent of phi? I have opposite over adjacent, okay? So that's going to be 2 times negative 13 over the square root of 231 over 1 minus negative 13 over the square root of 231 quantity squared. And so I've just got a little bit of simplifying to do here. Okay, let's do that. So I'm going to, at this point, I don't like having the radical in the denominator because of the way it's multi. This radical is going to get taken care of because of the squared, but this one I'm going to rationalize. So I've got 2 times negative 13, which is negative 26. And I'm going to rationalize, which means I have square root of 231 top and bottom here. And that's going to give me a 231 in the denominator. Then this is 1 minus, this is going to be squared. So I have 169, 13 squared. And then the square root squared just gives me 231. Okay, so notice how that whole 231 thing just happened to work out, right? Let me separate this out for us here. I'm going to multiply by 231 here, here, and here, right? Multiply by it. It's going to wipe out here and here. And that's going to leave me with negative 26 square root of 231 over 231 times 1, 231 minus 169. Right? So I have to just simplify that subtraction and we're good to go. The tangent is going to be equal to negative 26 square root of 231 over, let's see, 31 down and up, that's 62. Right? Okay. Now this can reduce, right? Because I can get a 2 out of here and a 2 out of there. So altogether I get a negative 13 square root of 231 over 31. Okay. So let's separate this right here. The cosine of 2 phi. Okay. For this one, I could pick any of 3 different formulas. I'm just going to pick the most obvious one, the 2 cosine squared of phi minus 1. Okay? Now, cosine of phi is the one that we used up here, right? The square root of 231 over 20. Okay, so that's going to be 2 times square root of 231 over 20 squared minus 1. Okay, so then this is equal to 2 times 231 over 400 minus 1. So then that is 462. You know what? Scratch that. I'm gonna reduce instead. The 2 over the 400 is gonna leave me a 231 over 200. That'll be even quicker. And for the 1, I'm gonna subtract 200 over 200. Okay? So then notice what I get is 31 over 200. Now, one final question. Sometimes what I'll even throw in with these is I'll ask, what is the quadrant of 2 phi? Because remember, 2 phi is a different angle than phi. It's some other angle. What quadrant is 2 phi in? Right? Because it can get kind of ambiguous up there. If I were to double everything, it would be between 3 pi and 4 pi. Okay? That's a couple of quadrants. Between 3 pi and 4 pi is quadrants 3 and 4. It could be anywhere in there. However, look at this. I have some information about 2 phi. I can see that the tangent is negative of 2 phi, and the cosine of 2 phi is positive. Therefore, 2 phi must exist in quadrant 4. Simply because I was able to compute those other 2 trig ratios, and in quadrant 4, cosine is positive and tangent is negative. I could not use this one because that's not the same angle. 1/2 phi is not the same as 2 phi, right? 2 phi, quadrant of 2 phi. Those are all talking about the same angle. Okay. So I hope this has helped you in your endeavors to study for the 3rd unit of our trigonometry semester. Don't forget to not just study these particular problems. Go after the skills needed to put all of these things together. Make sure you're practicing other problems that are similar of the same type but still slightly different. That will help you the most.